useful way of plotting this is on something called a scatter diagram. And that's where we just take the each symbol and plot it on, rather than against time, we're just plotting it on this XY axis. So we're seeing it, because the signal is just moving between minus 0.5 and 0.5, we're seeing these 2 points. This sort of diagram is called a scatter diagram and is pretty useful for evaluating modems when you're debugging them. You tend to draw quite a few of these sort of things. Modems that run, often we have a real-time display of this sort of thing to get a feel for the signal quality and how the modem's performing. So in a real world radio channel, the signals don't look quite as good. We have noise. When you get enough noise, it introduces a bit error. So in the next parts of the simulation here, we add noise at a certain signal to noise ratio. And this line here is where all this business here is just calculating the amount of noise we need to add. And here's where we add the transmit signal to the noise to get the receive signal. And if we do all that, once again, down convert the signal but with the additive noise, we get that. So what's happened is, because noise has been added to the signal, they're not little tight points on that constellation, they're bouncing back and forth. Now this is a signal to noise ratio of 10 dB, which is round about the limits of analog communication if you're transmitting single sideband or voice. But you can still see, for digital, the 2 points in the scatter diagram are quite a long way away from this zero line down the centre. Now if enough noise was added to this side to move one of these points over to this side, you'd get a bit error. And likewise, if enough noise was added to a point that should be here to make it move over here, you'd get a bit error. So as the signal to noise ratio drops, the spread in the scatter gets bigger, and eventually you start generating bit errors. A good modem will have less bit errors for a given signal to noise ratio than a bad modem. So that's the scatter diagram showing us the effect of adding noise to the radio channel. And at 10 dB you can still see there's no bit errors there. None of those have even got close to the middle line, which is pretty good for digital communications. Okay, in the real world, the transmitter and receiver are at different sites. They don't have exactly the same local oscillators mixing the signal up than mixing it down again. There'll be difference in frequencies of those two oscillators. So we can see the effect of that on the scatter diagram. So what's happened there is those points are being rotated around in time because of the difference in the two up and down converters. So they're sort of moving around. If that was in real time, we'd see them move in a circle. And eventually you can see some of these points have crossed this 0 point. So due to that frequency offset between the transmitter and receiver, they're not quite tuned exactly the same, we've started to get some bit errors. And that's, if you saw that on the scatter diagram, you'd know, aha, there's a problem with the frequency offset. Now how we fix that is we don't manually adjust the receiver frequency. We have an algorithm called carrier recovery or frequency estimation that automatically works out the difference between the two transmitter and receiver frequency and then adjusts that using some DSP magic. And that's called carrier recovery. Now also for a real-world system, what you'll have is the transmitter will have a D to A converter with a sample clock. It might be clocking out samples at a million samples a second. The receiver will have an analog to digital converter that's sampling the signal at, say, 1 million samples a second. But those clocks are at two different sites. They're running at different frequencies. It's just slightly off. There'll be different temperatures and things. So you'll see one will be a little bit out compared to the other. That means that the transmitter and receiver are at slightly different sample clocks, which once again leads to distortion in the modem and possibly bit errors. So the next step is I've simulated what happens when you've got a difference in the sampling timing of 10%. So the receiver's 10% difference to the transmitter in where it takes those samples. And once again you see that scatter. This example has no noise added to it or frequency offset, but the effect is exactly the same as adding noise. You get a noisier spread of points on the scatter diagram. And if you had too much of a timing offset, eventually, a point on one side would move across a zeros line and you'd get bit errors. So the way we correct for this is we have another algorithm called timing offset estimation, and that works out exactly what the receiver works out exactly what the sampling clock of the transmitter was, and uses DSP techniques to recover and correct for that. So the demodulators tend to be a fair bit more complex than the modulators, as you've got to estimate parameters like frequency offsets, timing offsets, and try and get them right. Those estimation algorithms aren't perfect, so you never get exactly those sort of perfect 2 points I showed you. You get little balls usually, and of course additive noise makes it all worse. But a good modem will maintain all that synchronisation right down to low signal to noise ratios and still give you good performance. So what we've just done now in DSP speak is we've built a binary phase shift keyed or BPSK modem. It's got raised cosine filtering, and we've simulated its performance over additive white Gaussian noise channels with frequency and timing offsets. That all sounds a bit scary, but when we move through it step by step, it wasn't too bad. A BPSK modem is the theoretical optimum modem in terms of you've got a watt of power, that'll get a better bit error rate than any other sort of modem. So that's the end of the basic tutorial, and happy to answer questions. Stunned silence. Oh, there's one.
Where do you stand on Keith's assertion that if you don't include forward error correction, you're an idiot?
I'm an idiot because there's some things that I don't put FEC into. Yeah.
He didn't hear it in context, so he can't comment.
Yes.
Where's a good place to start getting a grounding into the maths you need to understand?
Some of it is, I don't know. Good question. If you look at the script there, a lot of there is some complex maths involved, with complex numbers and things. That's about as tough as it gets, sort of year 12 complex numbers. Yeah, so year 12 text, I suppose. Yeah.
Sitting on some first year maths lectures like engineering or signal processing and other stuff.
Yeah, online first year comms stuff, some of this. Yeah. Yes.
Is development on your 3DV modem still going ahead?
Oh yes, although at the moment I'm playing with some other parts around the system, but the whole 3DV system is still being worked on quite a lot. I've got a talk on Wednesday where I'll talk about what I've been doing the last 12 months there. Yeah, been doing some embedded work and also working on some new schemes with forward error correction, so I'm not brain damaged, or with more forward error correction anyway. I use a little bit at the moment. And the other thing that's happening is a bunch of guys in the States with Bruce Perenz are building a VHF open source walkie-talkie running Android and codec 2. Yeah. I call it a white box rather than a black box because it's all open. And yeah, a few other things going on, but that's all I can remember off the top of my head. And I'll talk about some of those on Wednesday. I saw another hand. Yes? What sort of? FEC. Most of my work has been done with FreeDV, and I'm using a simple block code called a GoLay code, but only to protect part of the bits, the most sensitive bits in the speech codec payload. Yeah, so it's horses for courses. I came up for that sort of allocation based on the bits I had available, and now I'm currently working on some LDPC codes for a more advanced version of FreeDV, the FreeDV waveform. But I don't know much about. I know about modems and codecs, but I don't know too much about FEC. That's where I just resort to other people's code. Yes.
When you said that the BPSK modem was good in terms of having a lot of transmitter power, how would it...
It's good in power efficiency.
In terms of, power efficiency.
So with a given signal to noise ratio, you'll get a better bit error rate than virtually any other modulation scheme.
What sort of other schemes work better in other circumstances?
Oh, well, things like FSK will work better when there's, say, a lot phase distortion in the channel. Because binary phase shift keying depends on the phase, recovering the phase of the channel. And some channels, like, say, a HF channel, is not so great for preserving the phase of the channel. There's other implementation reasons why you might want to use another sort of modem. Phase shift keyed in general is complex demodulators and complex hardware. Mobile phones use something called GMSK, which is just easier to build, in particular transmitters and power amplifiers. So sometimes that's why you choose other. And there's various variants of PSK. I'm using BPSK, but there's other variants of phase shift keying as well.
Yeah, I've noticed that a lot of implementations, especially those that have data out in the air, use some form of QAM.
Your QAM is a form of phase shift keying.
Yeah.
Yeah, just with a more complex constellation. Yeah. Yes.
How does this translate to an actual antenna? I mean, I can see the digital part of it, and I can see the antenna part of it. How does what you're describing actually make it to...
So in there, there's the signal called TX, the thing that I plotted the spectrum of. If you fed that through to a D to A converter, you could drive an antenna with it. Maybe through a power amplifier first. Yes.
This is possibly a bad question, but when you started with your sort of standard digital binary 1 and 0 waveform, square wave, a basic knowledge of the frequency spectrum of a square wave means there are going to be all those
Yes.
modes. Obviously, you're filtering down to something that looks more like a sine wave. If you're starting with an actual sine wave, what options do you have for making, for transmitting binary data using, either phases or permutations of the sine wave?
Well, this is actually mathematically equivalent to using two different phases. 1 minus 1 are like cos of pi and cos of 0.
Okay.
So that's binary phase shift keying. You can also use quadrature phase shift keying where you have 4 phases or 8 phases, or you can combine the phases with amplitudes and have, say, a grid of 16 dots. Yeah, and they, as the points get closer together, you got a higher chance of a bit error because they're closer together, and there's less distance to go before you cross a decision boundary. But they carry more information, so the bit rate's higher. So there's all those sort of pros and cons to balance up when you design a certain modem waveform for a certain channel. Yes. Yes.
Just looking at the code there on the scatter plot, you're plotting the real and imaginary parts.
Yes.
What does the imaginary part represent?
It's just a way to plot. I'm sorry?
Can you repeat the question?
Oh, okay. The code has been inspected, and on the scatter diagram, someone's found that I'm plotting on the y-axis the imaginary part of the signal, and on the x-axis the real. The imaginary part is 90 degrees out of phase with the real, and it's a way of just conveying the phase of the signal through the maths. It's real and imaginary as in complex numbers. I sort of didn't want to, I'm not sure how many people know complex numbers and didn't want to go there. But it's just a way of handling phase in the maths as well.
So we're looking at amplitude and phase.
Yes, yes. Yeah, or an Argand diagram, I think they call it at high school or something. Yeah. Well, the spectral plots I did before were done with Fourier transforms, yeah. I converted from the time to the frequency domain using a Fourier transform routine. Yeah. Scatter plot, no. No, that's plotting complex numbers on an XY plane, effectively. Oh, yeah, I can't really... You got me there. I'll go look up the maths book. Yeah. I'm an engineer, I just know the formulas. Yes?
Yeah, have you got a best digital coding scheme for the data where you through the modems?
A best digital coding scheme?
Yeah, like, I suppose it's related to forward error correction, but different. I'm not familiar enough with it, but I know you can put the right digital bit through and it reduces the chance of...
Well, you can use forward error correction where you send redundant information to help correct for bit errors afterwards.
Somehow it reduces the number. It uses 5 bits to use 4 bits or something. You're less likely to get 2 the same in a row. I can't think of the right word.
It might be a line encoding sort of scheme. Often that's used on wireline stuff rather than radio, but yeah, that might be like the next layer up. This stuff's real physical layer stuff, and what you do is you.
I think you were referring to when you were talking about quadrature modulation, where the points on the plot actually represent a symbol.
Yes.
And that's,
number of bits per symbol, perhaps.
yeah.
Yes.
And then the symbol translates back into
line code.
If you're doing phase recovery and there's a long string of ones or a long string of zeros, it messes up your phase recovery. So you
With a lot of phase.
NRZ encoding.
Yeah, with a lot of phase estimation algorithms, they will get screwed up. But you can also put scramblers on the signal to keep it pseudo-random. That's another thing to do.
More about something like gray coding, where you map 16 bits on like
Yes.
on 5.
So that's like, this is a binary phase shift keying. If you have a higher order constellation, like say 4 points on that dot, quadrature phase shift keying, then they're often grey coded. So that if you get a single, if it crosses from here to here, you only get a single bit error. So you're probably thinking about like higher order modulation schemes. In that case, more than 1 bit per symbol is transmitted. I didn't make a distinction between bits and symbols, but each of those samples could convey more than one bit of information. Yes?
So how do you go from what you've shown us today to something like a modern DSL modem?
Okay, so a modern DSL modem is a multi-tone modem. Has a bunch of these carriers. I just showed one. It has them stretching from just over 3,000 kilohertz, just above the audible telephone line, right up to, I don't know, megabit hertz or something. And it automatically, it's got another software algorithm that can estimate the quality of the channel and which of those modem tones will make it through and not, and allocate power appropriately. So imagine 100 of these things running in parallel. Instead of all being at 500 kilohertz, they're offset a little bit. But yep, exactly the same stuff.
They're still essentially just very simple modems. Just
Bunch of modems in parallel but with some channel estimation smarts, because radio channels, you get noise and you get fading and stuff, but a piece of telephone wire can be really crappy and it can change all the time. But exactly the same principles. Yeah, you still got your carrier recovery, timing recovery. You're mixing. You can't send it at baseband along a telephone line because you've already got people talking, so you need to mix it up to a carrier frequency.
Would you only need to do carrier recovery on a couple of the channels? So
Yeah.
they should all be synced?
That's right, they should be synced. What you might do is also combine all the information from all the channels to get a better estimation of the transmit carrier. Yep.
You still get phase, stuff coming in and out of phase with frequencies on phone lines, like you do HF propagation. So.
Right.
Yep, it's a good example, yeah. Even your telephone, the old school telephone modems, fax machines, same sort of stuff underneath. Yes?
So what rate do you have to drive the ADC to transmit after you've done the modulation?
You'd use just at least twice the frequency of the highest frequency component and you modulate. So in that case, say 2 megabits, 2 mega samples per second. Or what you might do, I did the whole thing in DSP and you can do that these days. You could also output it at a lower frequency, then use an analog mixer to mix it up to, I don't know, microwave or something. Yeah. Similar principles are in your modems for your phone and your Wi-Fi, etc. Yes?
Just as a note, I saw a really nice graphic a couple of months ago of a full 28.8 kilobaud modem handshake and an actual the frequency spectrum, and each bit was or each section was identified, and then they'd have what these actual sections mean in bits and what they're just telling each other, and the whole conversation. If you look up the DSL, so modem handshake explained, I think it was. It's great if you want to get into that higher level of what they're actually talking to each other with.
Okay, cool.
So, yeah.
Nice. Any other questions? Yes?
Do you have a similar tutorial for things like PSK31?
No, but it's a similar. Yeah. Very similar. In fact, that'd probably be a pretty good example. Just to push this to a few more slides, we could probably show that because it's very similar. Yeah. And we could probably get it to the point where you can then hook it up to a radio and decode off air. Especially at those low symbol rates, 31 symbols per second. That simulation program I was using, Octave, would run in real time.